In this section of gases, we are going to combine all the gas laws we have learned so far and also learn about ideal gas law and some applications of it, because what do we do with it? More. We can do a lot more. Anyway, okay, so the gas laws that we have, we study the properties of volume, temperature, pressure, and moles in that. So once you've done all of this, then you can start looking at some other relationships in it too. So for example, we know about Boyle's law, Charles' law, and Avogadro's law, but we have not learned about the relationship between pressure and moles. Not that you want to, but if you wanted to, then how would you do it? So either you do it by, setting up your own experiments, or you can combine the gas law and then see if you can figure it out from there, and you will see that we can. So then we'll go ahead and manipulate it a little bit more, the gas law, and see how we can use it. So let's first talk about combining the gas law. Here are all the gas laws, right? Boyle's law, Charles' law, Avogadro's law. So when you look at all of these three laws, I've highlighted the volume here for you. So you can see that volume is one thing that is in all the three laws, okay? So now if we take the volume, or if we combine all of these, because the volume is consistent in all of them, this is what you will get, right? So volume is consistent, and then pressure is on the top, temperature and moles at the bottom. And then all of this is equal to a constant. Okay, so remember there is still a constant in all of these equations, and I didn't give you the constant because I said right now it's not important. Even now it's not important. Okay, I'm just saying that all of these quantities are equal to constant, because what I want to do right now is I want to study how you can study all of these relationships in an initial condition, and then if you change one of the values, then what happens in the final condition. Okay, so again, you're looking at initial and final conditions if you change one of the properties. So if you change the volume of the gas, or if you change the pressure of the gas, what's going to happen, okay, to the other things. So that's kind of what you study with this combined gas law, all right? The way we use the combined gas law is, you can either use the initial and finals, or you can use ones and twos. It's up to you, okay? So I just gave you the two, but it really doesn't matter which one you use because they're both the same, okay, in a way. And now you can see that all the relationships here, and let me point to this one because this is bigger. So in all of these, you can see that you can study the relationship between pressure and moles also now. Okay, so let me tell you one small thing here. And if you understand it, then it's really going to be good for you, okay? So pressure and volume, if you remember that, it was an inverse relationship, okay, which means if you increase the pressure, you decrease the volume. Volume and temperature was direct relationship. You increase volume, you increase temperature. Look at how we are putting them, right? So P times V is equal to constant. On the other hand, V over T is equal to constant. This is an inverse relationship. This is a direct relationship. So if something is a direct relationship, it's going to be the numerator and the denominator. If it's an inverse relationship, they are together. So here now, if you look at these values or conditions, now pressure and moles, it's on top of each other. So it's numerator and denominator. It means that it is going to be a direct relationship, which means what? If you increase the number of moles, you increase the pressure also, okay? This right here is Boyle's law. Pressure, volume and temperature is Charles' law. Volume and moles is Avogadro's law, okay? So now you also have a relationship between pressure and temperature. Again, if you increase the temperature, you increase the pressure, all right? So now you have all the relationships in one gas formula. And so it's really very useful. All right, so here is a solved problem for combined gas law. Combined gas laws are not very hard to do because you just need to figure out your initials and finals, and that's really the main thing. Okay, actually there are two main things for gas laws. One is, of course, knowing your initials and your finals. The other thing is your units. Okay, so you make sure that your units are good. All right. So I don't know if you want me to read the whole problem. It kind of gets boring, but still I'll go ahead and read it anyway. Okay, so divers working from a North Sea drilling platform experienced a pressure of 50 atmosphere at a depth of 500 meters. If a balloon is inflated to a volume of 5 liters at that depth, at a water temperature of 4 degrees Celsius, what would be the volume? So which means we're calculating volume of the balloon on the surface at 1 atmospheric pressure and temperature of 11 degrees Celsius. Okay, so the first thing you do is you identify your ones and your twos, okay, or initials and your finals. So here, if a balloon is inflated to a volume of 5 liters, and the pressure is 50 atmosphere right there, okay, at a pressure of 50 atmosphere, and the temperature is 4 degrees Celsius. So 4, immediately go ahead and convert it to Kelvin because you don't want to forget that. And then you figure out your finals also. The pressure then final is at 1 atmosphere and the temperature is 11 plus the 273, okay, to give you the Kelvin. And you're calculating the final volume of the balloon. So you can either use this equation as it is to set up your numbers and then isolate the final volume, or you can do like I did, which means I wrote my VF out first and then I will plug in all the numbers, because once I know what is my initial and final, I can do that here. Okay, now you can also do that in the problem. Okay, if you wanted to, you can just go ahead and mark all of these things here. So you can say, oh, okay, what would be the volume? So this is the final, and then this is the final, and then this is the final. Okay, so that way you can do that directly on the problem in case you don't want to write everything again, because yeah, it takes time to write everything, right? So, you know, just do it in the problem. You'll get comfortable, right? And hope now you are comfortable. Okay, and then you have set your problem. Once you've set your problem, if you want to cross out your units, you can. But you know, generally, if your formula is correct and your numbers are correct, your units are correct, your answer should be correct, okay, as well. So just make sure all of that is correct, and then you are on the right path. Okay, so ideal gas law. Ideal gas law is about combining the gas laws, but then what you want to do from there is remove that proportionality sign, okay? Because remember, in all of these laws, you have that proportionality sign. So we want to remove that proportionality sign to give us something that does not have a proportionality sign, which this one does not. Okay, this one and just kind of, it's putting V on one side and all the other conditions on the other side. So which means that we need to add a constant, right? So as soon as you remove the proportionality sign, you have to add a constant. Now we're going to have to worry about the constant, because at some point, you know, we need to study the gas law as a gas law and not just about initial and final conditions. Okay, that constant that we have just added here is called R, and it's called the gas constant. Okay, so it's going to be a constant number, and so now we can rearrange the equation. So it is PV is equal to nRT. If you want to name it, is PVNRT, but no, I mean, it's up to you. Okay, but PV is equal to nRT, another one of those equations like Avogadro's number that you will never, ever, ever forget. Okay, it's a very simple equation. But then the question is, what is R? Okay, and so for R, you need to calculate that, and to calculate the value of R, you need to know all the other values. Okay, so remember, PV is equal to nRT. So if you want to find R, it is PV over NT, which means you need to know all of these values. So pressure and the volume, and then moles and the temperature. In order to do that, you need to have some conditions you're working in, and those are called standard conditions. STP, standard temperature pressure conditions. Okay, so at STP, which is 0 degrees Celsius, 1 atmospheric pressure, and 1 atmospheric pressure. Now you have to work in consistent units, okay? So you can work in torr also, but you'll get a different value of R. So you want to be consistent as much as possible, okay? So here are the STP conditions given for us in all the standard terms, and this is the one I would like you to use all the time. These are the conditions I would like you to use. Temperature is 0 degrees Celsius, which is 273 K. Pressure is 1 atmosphere. Temperature, pressure. What are we studying? We're going to be studying 1 mole of gas, and the volume of that 1 mole of gas at 273 and 1 atmosphere is 22.41 liters. Okay, so that is how I would like you to remember these conditions. So let me go over that again. The temperature is 0 degrees Celsius, which is 273 Kelvin. The pressure is 1 atmosphere. We are studying 1 mole of gas, and under those conditions, 1 mole of gas occupies 22.41 liters of volume. So those are the STP conditions. Now, once you have these STP conditions, now you can plug in all of these into PV over NT, and so you multiply pressure, which is 1 atmosphere, by volume, which is 22.4, N is 1, temperature is 273. So essentially what you're doing is dividing 273 by 22 point, the other way around, 22.4 divided by 273. So what you end up getting then is the first value over here. That is the value of R that you end up getting. What are these other values of R? These are if you were working in different units under different conditions. Not different conditions as not different from STP, but like J stands for joules. So that is an energy unit. Okay, so it's a different kind of a thing. I would like you to just use this R for right now. If there is any other value of R needed, I will give that to you. I mean, I will give this one also to you. Okay, so, but hopefully by the time you use it enough, you will have memorized the number. Okay, 0.08206, or you can also say 0.0821. Even that is fine, because even that 1 over here is the 4th decimal place. Okay, so it's not going to matter a whole lot in your calculation. So what we are doing with this, okay, is we are trying to study the gas at a standard temperature pressure. We're coming up with a gas constant at standard conditions. Why can we do this? We can do this because we know that gases behave in a certain way under certain conditions. Okay, so under STP conditions, they behave like this, which means they occupy 22.41 liters of volume if you have 1 mole of gas at 273 K and 1 atmospheric pressure. That's how it goes. This law that we come up with is called the ideal gas law, and ideal gas law means that all gases are going to behave that way. Okay, so the ideal gas law means that this is how gases should behave ideally. Ideally means in a hypothetical situation, which is for us it's realistic also, but there is also what we call real gases, and real gases can behave different than the ideal gases, because ideal gases are ideal, right? This is how one should behave, but not everybody behaves that way. Even we don't behave that way, right? Ideal is very different than real behavior. Same thing with gases, but for that you need to have extreme conditions, okay? For us also, you know, our behavior changes when we are in extreme conditions as well. But anyhow, okay, so that is going to be our constant, okay, that we deal with in ideal gas law. All right, so here is a problem for ideal gas law. A cylinder with a volume of 68 liters contains oxygen at a pressure of such and such kilopascals at 23 Celsius. What is the volume of this gas at STP? So pressure is given to us in kilopascals. So first of all, just convert that to atmosphere, because nobody works in pascals. So convert that into atmosphere, convert the temperature into Kelvin, and the volume is given to you, right? but they're asking what is the volume of this gas as STP. So this is a combined gas law problem because you have an initial and then you have a final condition. Okay, and so studying these initial and final conditions is using this formula. The reason I have this instead of an ideal gas law right now is because I need you to understand that when you read a problem, you should know what formula to use, okay? Because you need to know whether you're using combined gas law formula or an ideal gas law formula. So whenever you see something like an initial and a final, or different sets of conditions, then make sure you're using combined gas law. Okay, so which is this then, and then you go ahead and figure out what you need. So you're trying to find out the volume at STP. So STP conditions are 1 atmosphere and 273 Kelvin. Okay, and the volume for that would be then 9,850 once you do the calculations. Okay, again, I've crossed out the units for you so you can see that you're left with liters. Okay, again, here you are using combined gas law. Why? Because you have initial and final set of conditions. All right, so here is the ideal gas law. So for an ideal gas law, calculate the pressure of a gas if 0.214 mole occupies 338 milliliters at 32 degrees Celsius. So first of course, here are your numbers. Okay, so the moles are given to us. Volume is given to us in milliliters. So convert that to liters. Temperature, convert that to Kelvin. So 32 plus 273. I added the 0.15 and you can see that I've been working with and without the 0.15 and it doesn't matter. For you also, you can use whatever you want. I'm fine with it. So we are trying to calculate the pressure. So here is PV is equal to nRT. Go ahead and plug in your numbers. So isolate the pressure if you want, you know, so this is what I do all the time. You can see that, so I know that I have to calculate pressure. So I rearrange my equation. And then plug in all the numbers. Okay, again, as I said, if your equation is fine, your numbers are fine, your units are fine, your answer will be fine as well. Okay, and here is the atmosphere, and I have also crossed out the units for you so you can feel happy that okay, it's all good, it's all good. Another one for ideal gas law. So this 150 liters container has a pressure of 17.1 atmosphere, 23 degrees Celsius. What's the mass of nitrogen now? So we are given the volume of nitrogen. We are trying to figure out the mass of nitrogen. To figure out the mass of nitrogen, you need to find the moles of nitrogen. So you have the volume given, you have the pressure given, and then you have the temperature, which the temperature again 23 plus 273 will give you then the 296. And so once you have that, you're calculating for moles because again, you have to calculate mass, right? So for mass, you need moles. So isolate the moles and then PV over RT. So go ahead and plug in all that. You get your moles, 32.5. And then all you have to do is convert those moles to grams. And this is grams of nitrogen. So the molar weight of nitrogen, N2, is 28. Remember, not just N, okay? N2. And that's it. Okay, step by step, step by step. Okay, so one of the other things we can do with the ideal gas law is we can actually rearrange the gas law in order to figure out the gas density and the molar mass also for any gas. What's given here is kind of shown you how we actually get to this equation at the end. So I need to just kind of go through it. You don't need to know the derivation, but you know, I'm just going to explain to you how I got here. Okay, so when you have your PV is equal to nRT, if you rearrange that equation to N over V and then P over RT on the other side, okay, then N over V, moles over volume. Okay, that's what you have on one side, and then you multiply both sides with molar mass. Molar mass is grams per mole. So grams per mole, grams per mole. So what happens at that point? This is grams per mole. So the mole gets cancelled out. So then you're left with M and V only, okay, on one side. On this side, you have everything, all right? And so once you do that, M over V is density. Okay, so that is mass. Grams over volume is density. That's what's left over, okay, on this side. So I can write that for you if you feel like that will help you. So molar mass is grams per mole. So this was grams per mole, and then mole and mole gets cancelled out. So you're left with grams over volume, and grams over volume is density. Okay, that's what it is. So on the right hand side, you still have the PM and the RT, right? That's all there. So that's how you get to the density of gas. Now here, just remember, density of gas is grams per liters, okay? When we were working with density before, usually it is grams per milliliters, but because gases occupy so much volume that we end up using gas per liters as the density unit. Okay, so just be careful of that. Other than that, everything is fine. Okay, so this is an equation you will need. And then if you rearrange the above equation, then you will end up getting this equation, which is how to calculate the molar mass. Okay, so use whichever equation you need for whatever calculation you need. Okay, again, very simple. Whenever there's an equation, my life is good. Like, okay, just tell me what the equation is and I can plug in all the numbers and get the answer. So what is the density of methane gas at 125 degrees Celsius and 3.50 atmospheres? Okay, so the molar mass of methane is CH4, that's mm over here. Okay, so 16.04 grams per mole. Pressure is given to us, and then temperature is given to us, and again change that into Kelvin, so that's 398 Kelvin. So we're going to go ahead and use the density calculation here, and density is MP over RT. So the molar mass we know, pressure we know, R of course we know, R is a constant, and then temperature we already know. So you can cross out the units if you want to, but again, if you're plugging everything right, your units should be grams per liter at the end. Okay, so do the calculation, should come up with the answer. Honestly, as I said, okay, very straightforward. So here is calculating the molar mass. So calculate the molar mass of a liquid which when vaporized at 99 degrees Celsius and 716 torr gives 285 milliliters of vapor with a mass of 1.103 grams. Okay, so the mass is given to us this time. Temperature, again, convert to Kelvin. Volume, convert to liters. Okay, I mean, like, all we're doing here is just unit conversions, okay, in the beginning. 716, convert to atmosphere. Why do we have to do all this? Again, we have to do this because of R. Okay, R is our gas constant, and we want to make sure that all the units that we are working with are the same as in R that we are using. Okay, and R, we will be using only this R. So this is it. So you have liters, atmosphere, mole, Kelvin. That's all you're working with. Okay, all right. So what are we doing here? We are calculating molar mass. So molar mass then is equal to density RT over P. Now we are not given density, are we? No, we're not given density, but we are given the mass and we are given the volume. Okay, so we can go ahead and calculate the density of the gas, which is mass over volume. So we're just going to go ahead and plug that right into the equation. Okay, so we don't have to do a separate calculation. You can if you want to. Okay, just remember to convert the volume to liters, which we did over here. All right, so if you feel like, you can do the density calculation separately and then plug it here, or you're doing it right here also. Okay, it's up to you. Again, just make sure you have, again, the right units, the right thing, that's all. Okay, whether you do the calculation here or here separately, it's the same thing. Okay, because eventually you're going to have to multiply that by R and T and divide it by the pressure, and then you get your answer, okay, of the molar mass. So that's just using the ideal gas law and kind of manipulating that in order to get density and molar masses of gases. I think that's it then. Okay, all right, so combined gas law, ideal gas law, and standard temperature pressures, STPs, really good.